Greetings, ladies and gentlemen. Today I'm going to introduce our work named Expert Advice Problem with Noisy Low-Rank Loss. My name is Liu Yaxiong. Now I'm PD researcher in RIKEN-AIP Computational Learning Theory team, leading by Professor Hazan. Okay, this presentation is composed by the following parts. Firstly, I'm going to introduce some basic definitions in the titles. What is expert advice and what is low rank. Then I'm going to interpret the solution of these problems, especially in the fourth section that is the main result of our work. Then it follows the experiment and some notice about the future work. Okay, let's come to the first part. This is about the definition of prediction with expert advice, which is a very famous online learning model. And in this model, there are two objects in this framework, algorithm and the environment. It is a sequential decision-making systems for round small t from 1 to capital T. In each round, firstly, the algorithm gives n-dimensional distribution Wt, and then the environment returns a loss vector Lt. It is in -1 to 1 cube and dimensional. I want to give two notice about these issues. Firstly, the loss vector can be adversarial, which means it is not necessary to be IID distributed from underlying distribution. And second is that for each round, the algorithm firstly gives the distribution and then receives the loss vectors. So this is a prediction problem. Then for each round, the algorithm incurs the loss, the inner product between prediction distribution Wt and the loss vector Lt. The goal of the algorithm is to minimize the regret, which is a difference between the simulative loss and the global optima in hindsight. And as we mentioned, this is a very traditional online learning model, which has been researched for decades. I think one of the very famous algorithm is called Hedge algorithm in point paper in last century. It gives upper bound to this regret. Meanwhile, this bound is also tight, which means that the upper bound and the lower bound only differs from each other with a constant parameter. And this regret is theta as square root of t times log n. N is the dimension of the loss vectors. Okay, now let's come to the noisy low rank structure. Firstly, we introduce what is a low rank structure. We introduce this issue with an example. Let's consider movie recommendation systems. There are n different movies, and we evaluate these movies with d different factors like music, casters, stories, directors, and so on. And then there are t different users. For each users, we represent them as also a d-dimensional vector Vt. And we can say that each vector, users Vt, they will evaluate these n movies with inner product as ui times Vt. So in the loss vectors Lt, the ith entry of the vector represents the negative scores of user t to the movie I. So in this case, if the environment is in this way, so the regret now can be seen as the expectations of the simulative negative scores from the algorithm and the favorite single movies for all the users. So now, as we mentioned before, that there are although there are n movies, but there are only d different factors for these movies. So we can call that the loss sequence t from 1 to large T is a d rank loss. So this is not a very straight definitions. Let's come to a more formal version of this loss. Okay, although the loss vector LT is an n-dimensional vector, but actually all these loss vectors are from a D subspace, a D-dimensional subspace from the n-dimensional space. So given matrix U, which is the rank of this U is D, we call this as a kernel of the D-dimensional subspace, which means that each loss vector can be seen. It is linear combinations of in this D-dimensional subspace. Okay, and if the rank of U or the kernel, the rank of the kernel is very small, much smaller than the dimension of the loss vectors, we could call the loss sequence as low ranked. But precisely how small this D should be? Well, from the following part, we would say that D should be in the order of square root of log n. It must be quite very small. And frankly speaking, the noisy low rank loss is straightforward, that for each low rank structure U times Vt, we add arbitrary noise vector epsilon t, and now we can have a noisy low rank loss. One thing I want to mention is that no matter how this noise vector is, the D rank loss vector has been totally damaged. So if we have a review of our movie recommendation systems, we can say that now the negative scores of user I to the movie, user T to the movie I will added noisy part epsilon Ti, although all the epsilon Ti is bounded with L2 norm. I think it is more natural because there will be some interpretations of the users. There have some influence, like emotions for him to his attitude to the movies. So if we say the rank of the loss vectors is n, and the noisy part disappears, then our setting recovers the original expert otherwise setting that all the loss vectors are arbitrary. And if the epsilon is 0, and which means that there is no noise, it is recovered the low rank case. Okay, now we can describe the definition of expert otherwise problem with noisy low rank loss. Fix a full rank matrix U. For each round, algorithms firstly makes a prediction WT, and then the environment gives the loss vector LT. It is composed by two parts, the low rank parts U times Vt and epsilon T as a noisy part. One thing that we need to mention that the algorithm only receives LT, so the algorithm has no information about U or epsilon T, but algorithm knows the upper bound of L2 norm of the noise. And then the algorithm incurs a loss with respect to the noise low rank loss LT and its prediction WT as inner product. And the regret is also defined with respect to the noisy part, noisy loss vectors, LT. Then I will show the location of our work. This online learning expert otherwise problem with low rank loss is a quite new topic rather than the original problem. And we can say that if the kernel U is known to the algorithm, then the result is quite nice that, for instance, it is tied as square root of d times t, or even though it is noised by epsilon, it has also a square root of d plus epsilon t bound. And if the kernel is unknown, then the upper bound is d times square root of d. So our work is to consider the case that the kernel is unknown and the low rank structure has been somehow damaged. And this is our work. We gave the regret bound as square root t times d plus the second part. And we can say that if the epsilon is quite small, for instance, it's in order of 1 over n, and the rank is in the order of log n with power 1 over 3, our work can be seen as accurate than the Hedge algorithm. Okay, let's have, before to our main result, I want to have a review of the previous work about the noiseless case. And the basic algorithm used for both noisy and noiseless cases online mirror descent. And we will involve the matrix norm here. And this theorem shows that the regret is respect to two parts. So firstly is bound to the matrix norm of the domains. And the second part is dual norm to the loss vectors. This is about a little bit technical part that we will use minimal volume enclosing ellipsoid, which means that we will, as the input of the k different independent vectors and intersect it with L infinite norm, it will output ellipsoid, which contains this subset of the loss vectors. Meanwhile, constant times this ellipsoid is contained by the previous mentioned subset. And we will use this ellipsoid M in our result. Okay, this is a basic reduction if the kernel is known. Compared with the Hedge algorithm, the decision set bounded with L1 norm is 1, and L infinite norm is 1 actually. Then with the low rank case, the decision set is bounded with respect to the rank of the kernel, and the loss space here is bounded by 1 actually. So this theorem shows that if the kernel is known, according to online mirror descent, the regret is given as square root of d times d. So we can say that in this case, the regret bound is highly related to the rank of the loss sequence. And so if the kernel is unknown, the result is also not difficult. We can use inductions that firstly, we show that we assume that the kernel is empty set. Once the received loss vector cannot be represented as the current subspace, then we just add this new loss vector as the new kernel. Then it gives the regret bound as d times square root of d. However, this algorithm fails if, as we mentioned for the noisy case, because in this case, the rank of all the noise vectors is not d anymore. It's the rank expands to n. It's the full rank matrices. So if we run the previous algorithms, the result would be n times square root of t, which is too large for these parameters. And Barman in 2018, they gave some algorithms to solve the case that the kernel is known but noised by the noise vector. So our setting, we assume that the noise is given to corrupt the low rank structure. Meanwhile, the kernel is unknown. So how could we approximate the true kernel? This is one of the central problems in our paper, and we need to solve. In principle, we will give our selection criteria for selecting the receiving loss vectors. There are actually two criteria. Firstly, we will make sure that the loss vector is long enough respect to the L2 norm by involving a parameter sk. And secondly, we will choose that the loss vector is far enough to the current span space, which by involving another parameter gamma k, which means that we will select the loss vectors, which is long enough, and it is highly independent to each other to compose or to approximate the true kernel U by UK theta. And we can update the k by the receiving loss vectors until then. So compared with the previous work, we can make sure that firstly, during our selection criteria, the algorithm will only update it for the approximate kernel for at most large k times, which we can guarantee that this capital K is smaller than the true rank of the loss vectors. So now we can make sure that the decision set actually is bounded by the collected loss vector number of collected loss vectors, and the loss space now is bounded by in this way, mk is corresponding to the parameters sk and gamma k. Therefore, multiplying the mirror descent algorithm, we can get the regret bound in equation 7. And in this experiment, we show that with different noise, the performance of our algorithm and Hazan's algorithm and Hedge algorithm, we can say that if the epsilon is 0 without noise, our algorithm actually performance is same as Hazan's algorithm. And if the noise exists, our algorithm performs much better than Hedge algorithm and Hazan's work. And with different n, which means with different number of experts, our algorithm performs also better than Hedge algorithm, for instance, with epsilon is 0.8. In the future work, we hope to remove the parameter n in the regret bound, or show the lower bound must contains n, or we hope consider other kinds of noise vectors, for instance, sphere loss vectors, or the loss vector is sparse. Okay, thanks.
Okay, thank you very much. Are there any questions? Then let me start. So actually, I wanted to ask a question about experiment.
Okay.
So like t equals 1000.
Yes.
Is it large enough for the theory to be reliable?
Yeah. Yes, this is just a toy example, actually. Actually, during the programming, our algorithm, it takes much time than other algorithms. So this is just a trend for the experiment. Actually, if t is larger, I think our algorithm can also perform us because we can offer an theoretical regret upper bound, actually.
So then when t is 1000, maybe it's not big enough. Then, so perhaps error bars are quite large?
Yes. Actually, the theoretical result shows that the error should be not very large. So we can have this regret bound. But I think if, as we can say here, if epsilon square is bounded by the minimize of this part, and actually in our case, the d must be in the order of square root of log n. So I do believe that even the epsilon as a noise is a little bit large, our algorithm can also perform as not worse than Hedge algorithm or Hazan's result.
So of course, this is a theory result, but so in practice, so how like useful the upper bound is?
In practice, I just suggest to running our algorithm with Hedge algorithm parallel, because we cannot make sure that what's the rank, the number of the rank in other ones. So our algorithm can perform us only when the rank is smaller than square root of log n. Then the low rank algorithm or the low rank structure effects. Otherwise, Hedge algorithm is better.
I see. Okay, thank you. So Chibin.
Yeah, I have a question. So when you learn the kernel, when the kernel is unknown, I think
yes.
you expect to have low rank, which means smaller d. I'm wondering, how do you learn the optimal d, optimal rank? And another question is there any relationship with low rank matrix decomposition?
I think about the first question, our algorithm is designed for the case that there is no prior information about the kernel, which means that at the beginning of the algorithm do not know the rank of the kernel. So the D can be expanded to N, but our algorithm also can performance. But as I mentioned before, if the rank of the loss vectors is not so low ranked, actually, for instance, the rank is half of n, then I suggest to use Hedge algorithm. Our algorithm only affects when the rank is very small, and we can guarantee theoretically that the updating times is bounded. It will not larger than the rank of n, the rank of the kernel. And as for the second question, I think it will be applied somehow in the proof of giving the bound to the the dual norm of the loss space with respect to the matrix decomposition. Here it will have some in the proof of this part, I think the matrix decomposition will be applied here. Does this answers your question?
Yes, thanks.
You're welcome.
Zhao Kai.
Hi, thank you for your talk. I have a question regarding your previous comment on running parallelly the Hedge algorithm and your algorithm.
Yes.
I'm wondering if we can have I'm wondering if we can have a method that no matter how large D is, we can perform optimally, which means that if D is very small, then it will achieve the regret bound you give. And however, if D is larger, for example, in the order of capital N, then it will automatically recover to the Hedge algorithm, the bound of the Hedge algorithm. In this way, you don't need to run parallelly two algorithms, and you will have one algorithm for all the cases.
Okay, this is actually, I think, nice future work direction. Actually, if we're running a meta algorithm with experts, as there are two experts, one is our algorithm with low rank, for instance, Hazan's algorithm. Another one is Hedge algorithm. So in this meta experts up predictions, I think the result can also convergence to the best case of either two situations.
Then can you briefly explain how this meta algorithm choose between the predictions from these two sub algorithms?
Okay. Let's consider the how to say the expert advice of this meta algorithms. And we can set in this meta expert advice, we can set two experts, only two experts. One expert is giving the result with respect with the Hedge algorithm, and the second expert gives the result as a low rank algorithm, for instance, our algorithm or Hazan's algorithm. Then for this meta expert advice, we can use Hazan. We can use Hedge algorithm, which will make sure that the best choice has only square root of t difference to our choices.
Okay, I see.
There is only log two difference because the number of experts too.
Implementing the meta algorithm by a Hedge algorithm can automatically choose which one is the best, and the additional cost won't be too large.
Yes.
Right.
Yes.
Thank you so much.
You're welcome.